Good morning. I hope you're enjoying the course. In today's lecture, we're going to discuss the tremendous potential of quantum computing. I mean, why are we spending so much time and effort in understanding this technology? We need to really be motivated to understand where it's going to lead us and society in general. I think the first thing to understand is that a quantum computer computes exponentially as opposed to linearly. And that's a huge difference. To give an idea what that sort of means, if you imagine a huge beach ball and then getting a very thin pencil and on the top of it, just putting a dot, then turning it over and putting a dot on the bottom, that's what digital computers use at the moment. The top dot is a 1, the bottom dot is a 0. And that's how digital computers work, basically. But the quantum computer, with the beach ball analogy, imagine all the dots around the exterior and then slice it up and put all the dots, micro dots on the inside. And dots everywhere. And you can imagine we are talking an infinite number of dots. So with the classical computers, they can only address the top dot and the bottom dot. With a quantum computer, it can address all of the dots throughout the whole beach ball, if you like. And that the beach ball analogy is what a block sphere is, B-L-O-C-H, and we will cover that during the course. So the quantum computer can do that many more times of computation at the same time. And that's just, it is incredible. We really do have to thank Richard Feynman in the 80s, who was the first person to look at harnessing this energy, this amazing quantum phenomena, harnessing it, even though we don't understand it, we know what it does, and we know that it does it every single time. So we can harness that power. So what does that mean for society? And there's a number of things. The first of all is factoring. And factoring is merely being given a number and being able to work out the two prime numbers that multiply together equal that number. And you may think, who cares? But actually, all of our cryptography depends on factoring. There is an encryption system called RSA, named after the three inventors of RSA. Now, RSA is used throughout the world because, as I may have mentioned before, it would take a classical computer, the fastest supercomputer we have on Earth, the IBM Summit out at Oak Ridge. It would take it literally thousands of millions of years to decrypt RSA. It's like when you ask a computer to multiply two numbers, it does it instantly. But when you ask a computer to actually discover which numbers multiply together equal this prime number, and of course this prime number is hundreds of thousands digits long. So if I said to you, well, the two primes that multiply together equal 15, you would get 3 and 5 pretty quickly. But if I gave you a 1,000 digit number, whoa, that might take it slightly longer. And the computer actually does, is it 1 times 1? No. Is it 2 times 1? No. Is it 3 times 1? No. Is it 4 times? And on and on. And that's why it takes so long. It can only do one great big blast, cipher blast to try and decipher the code. Whereas with a clever algorithm, a quantum algorithm written by Peter Shaw, who's still alive, I actually have messaged him to and fro on Quora. He and I both answer questions on quantum physics on Quora. I urge you to go there on any subject, actually. Quora.com. I believe Quora, if my Latin is correct, means question. So you can ask questions on anything, but when it comes to quantum physics, I get asked to answer about half a dozen a day. The same question, written slightly differently, to be honest. But Peter Shaw's on there, so he devised Shaw's algorithm, which is the manipulation of quantum algorithms, quantum gates. You must remember the observer effect. So we're not allowed to look or measure the qubit at any moment in time. The qubit, just to remind you again, is the photon or the electron that we are measuring. We indirectly measure it. If we actually measure it, it collapses the wave function. We'll get more into that at the moment, but just sticking with the potential. Shaw's algorithm can decipher RSA virtually instantly, depending on how many dots on that beach ball. I might add that when we get 300 beach balls and link them together through entanglement and superposition, we will be able to address the same number of atoms there are in the universe. And that comes to another potential, which I'll tell you in a second. But literally, RSA can be broken by Shaw's in seconds. So what would literally take thousands of millions of years, and the fastest computers of today, would take 6 seconds with Shaw's. It's amazing. The FBI, CIA, or mafias throughout the world are all aware of this and all catering for this. I might add that RSA can be replaced by quantum cryptography, which gets us back to a level playing field. You can't intercept a quantum message. At least if you do, you will collapse the wave function. So it's impossible for somebody to hack into your transaction. So it's very interesting. So you can see the potential in the financial world is absolutely huge. Secondly, the one mostly hears quantum computer being potentially incredible for is medicine. At the moment, what large chemical companies do, and microbiology companies, they try to simulate what chemical process takes place when they introduce a medicine into a body, or manipulate the DNA structure. How will that done? The mitochondria and every aspect of the body, and it's impossible to do. This is another case of an intractable problem for a classical supercomputer. We simply can't simulate how the genes will interact with each other because there are so many and because it's exponential. So how genes it's called gene folding, how the electrons in the chemical molecule interact with each other. After we can measure now with our fastest supercomputers up to about, I believe it's 4 or 5 seconds. It's in that area, and obviously you can't see any benefit or anti-benefit in that short space of time. So the field of medicine is going to change enormously because we can test out and simulate the chemical reactions. The third thing that I was alluding to before, when Feynman said we can harness these quantum phenomena, the other thing that quantum computers are going to be wonderful for is actually simulating nature, simulating quantum physics itself. Now, quantum physics is the basic law, the fundamental law of the universe is quantum physics. There's no question about that. As I say, you're a complete quantum object, so am I, so's everything in the background. It is truly amazing. It's amazing, and it's absolutely counterintuitive that the quantum world is so difficult from the classical world that we see. It's amazing that all these things are going on at the quantum level, but it's true. But we have no way of really measuring it to the nth degree, again, because it's the exponential world. But actually, a quantum computer can not easily, but can measure quantum fluctuations, especially quantum fluctuations at the beginning of the universe, when something came out of nothing or whatever. Let's not go into the creation stories, but something certainly happened. And if we take the Big Bang and simulate it, we've not really been able to do that, not to the nth degree. And a quantum computer will be able to do that. Again, I have to stress the exponential nature of qubits. So when you get multiple qubits together, they are exponentially capable of addressing, think of the beach ball and all the one and the top and bottom dot, and then all of the others inside and outside, exterior and interior, millions and millions and millions of little dots. And they can be, a qubit can interact with other qubits, and through the phenomena which we don't understand of quantum entanglement and superpositioning, we can manipulate them all to give us an answer, which is then fed back to a classical computer. So all of the computation is done on a number of electrons, which a qubit is an electron or a photon. Now, once that number gets to 300, we actually have a way of mapping every single atom in the universe. The recent Google supremacy wasn't a fully blown quantum computer, but it was a physical wrapping around of an electric current, forming 50 at absolute zero, forming 53 qubits. So even now we're playing around with 53 qubits. So yes, it's absolutely unbelievable. And possibly there's other things like anything to do with simulation. weather simulation, and again, all modeling and simulation is wonderfully done on a quantum computer. But I think the most important potential of a quantum computer is something that we haven't thought of yet. It's something someone out there, hopefully someone doing my course, will end up writing a quantum algorithm can do something weird that we have not even imagined. And I'm not being melodramatic here. What the ideas and concepts for the use of quantum computing has actually been pushed to one side, because the important thing is to get the technology working, and because of the hardware and software issues, it's very, very difficult. When you're talking at an atomic level, it's amazingly different. But one thing is for sure, classical computers are not going to get any bigger. Moore's law has almost reached its zenith. We now get interference if we make these integrated circuits any smaller. So I think you can see the incredible potential for this incredible phenomena. Please carry on and enjoy the course. Talk to you soon.